Hello, my AP Chemistry Wonders. This lesson will teach us about what we'll just refer to as Q, but it is formally known as the reaction quotient. When we are dealing with a reversible reaction, the goal of the reaction, because it's what we experience, is to get to equilibrium. So, depending upon where we're starting, we know that we're going to be making more product or making more reactant until we reach the concentrations that we insert into K. And we know that K is constant. That once we've reached equilibria, so if you imagine our water bin activity, and if we are favoring product and we have more water in that bin, it seems that it's at a standstill because we have an equal amount of change in both directions. But it is going to remain there. And we'll learn with thermodynamics, it's actually a position of lowest Gibbs-free energy. We'll find out. And so energetically, it's the place to be for a reversible reaction. And so unless we stress it or change the reaction in some way, it will remain at equilibrium. So the goal for a reversible reaction is to reach those equilibrium quantities that deliver what we evaluate to be the K expression. Okay. So we understand that K is only found with equilibrium concentrations. We could input other concentrations at other times outside of the equilibrium position, but then we can't call it K. What we call it is Q. So Q is the same equation. It is the ratio of concentration of product over concentration of reactant or reactants, and that, of course, is understanding that they're gaseous or aqueous. But if we're not at equilibrium, or we're not sure that we're at equilibria, then we can't call it K. So we call it Q. So Q is just any other concentration other than the equilibrium, or if we're not sure if we're at equilibrium or not. So this screen shows us, okay, same equation. It's an application of the law of mass action, but if we're not sure we're at equilibrium, okay, it's Q then. So, if we take a look at this graph, which we can see when the concentrations have leveled off of these different species, then we're at equilibrium. So, inputting the concentrations beginning at time of 20 seconds would yield K. But prior to that, anywhere there, it would be Q. It would be Q. All right, so what is the value? Well, if you take a moment and read this slide. We often don't have enough information to know in what direction do we need to move to get to equilibria. Okay, so we know an equilibrium problem begins with the equilibrium reaction, and we know we write the K expression to the right, and we proceed with our ice. Now, a lot of times we are told some initial amount, and then the information guides us to let us know, okay, are we shifting right to reach equilibrium? Are we pouring more water in the product bin, or shifting left, pouring more water in the reactant bin? And we know then that will lead us to the change line. Sometimes we're given information about equilibrium quantities or something else that lets us know, okay, we're making more product or making more reactant compared to where we initially start. but we may only know a starting quantity, which we'll just call initial. So into our bins, we're starting, especially if we start with a bit of everything. Now, you also know that if you don't have any product, well, of course, to get to equilibrium, you're going to make that. Or if you're missing one of your reactants, you're going to shift left to make that. But what if we start with a bit of everything? How do we know? Well, that's where Q comes in. So most times, we can evaluate the Q expression to reflect initial quantities. Okay, we're pretty sure we're not at equilibria. And remember, whenever we put that little zero as a subscript following a formula, then that means initial. So what we can do is plug in these quantities to judge, okay, are we at equilibria? Or do we need to shift right or shift left to get there? Okay, so if you're given initial quantities and you plug them in, and the value you get for Q equals K, then ding, 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 you are at equilibrium. You stay put. Your reaction is already there. But most times, we need to shift right or shift left. So, if you know your value of K, and you find the value of Q by plugging in these quantities, and Q comes out to be a greater numerical value than K. Remember, it's product over reactant, product over reactant. And so if Q is greater than K, we have a greater numerator than we should have, or too small of a denominator. So what we're going to have to do, we have too much product. So if Q is greater than K, we will shift left to reach equilibria. And so then we know we are going to be making reactant and then consuming product. So we'll be making more, and of course it will be per the coefficients, the mole relationships. However, if Q is less than K, we need more product. So this then, we would shift right to reach equilibria. And then we know that we would be adding to the product side and subtracting away from the reactant side. I have some great visuals that I hope will also communicate these. And so here, now, of course, how strange that, Q equals 0 and Q is infinity. So we're talking about like minuscule Q. Well, then pretty much we just have reactant. So yeah, we're going to be making product. And if it's infinite, well, that pretty much means we have no reactant. We just are starting with product. But usually we are dealing with what's shown to us in the last two lines there. I really like this graphic, and the dotted line is equilibria. That would be the quantity of K. And if Q is less than that, we are moving right, making more product. And then the bottom one, if Q is too great, we need to decrease it. So we'll be shifting left to reach K. This is another presentation of the, same kind of graphic. I like that, they have the ideal in the middle there. So that's what your reaction is trying to do. Your reaction is trying to get to equilibrium, to have the red bar and the green bar meeting the blue line of equilibrium. Well, if Q is too small, we are going to move toward right. And then if Q is too big, we need to move to left. So whatever kind of visual helps to communicate this, we definitely want to go with it. So I'd just like to end by looking at actually a specific example from your student note packet. All right. So we have to know when we need Q, and then how do we find Q, and how do we apply Q to solve equilibrium problems. All right, so digging in, we know we need our reaction first. Carbon monoxide, and we know at room conditions, gas, but oh my gosh, we're 700 Kelvin. That's definitely going to be gas. Reacts with steam. Notice they're telling us water in the vapor state to produce carbon dioxide. We know gas, and hydrogen. We also know gas. Okay, just going to make sure we're balanced and we're good. All right, next, our K expression. And okay, we are given the equilibrium constant, which we would definitely assume is K. And then I see I have moles and liters, so I know I'm dealing in molarities. So not Kp here, even though they're all gases. Okay, all to the first power. Nice. And we actually are told the value is 5.10. So we know we're, favoring products slightly. Oh. Okay. And I know, nice. Okay, and what the problem is ultimately asking for is calculate the equilibrium concentrations of all these. So we want our E. Okay, so it says, we are adding 1 mole of each to the 1 liter flask. And we know an ice table most appropriately has molarity values. So mentally, we can just do 1 mole divided by 1 liter. And that means we are starting with 1 molar of everything. Okay. Now, we know if we have 0 of something, we're going to shift to make it. And if we'd be given a later quantity, that could help us inform us if we are adding more product or adding more reactant. But we're not told anything else here. So, now I know with these values, we can just mentally make the call. But we should show the work. Show the work. All right. So, are we shifting right or shifting left? Let's forecast with certainty. We're going to need Q. So, same equation. I am going to go ahead and denote that, yeah, we're not at equilibrium because it's Q, but, I'm calling these initials. That's what I'm plugging in. All right, and I definitely understand, again, why are we plugging in 1 molar, and we're going to get 1, but we're going through demonstrating that we understand it's the problem solving and the logic that we're applying. All right. And we know our value is going to be 1. So, Q is less than K. Well, where do we go from there? So we know that we need more product. We need more product. If Q is less than K, our numerator is not as big as it needs to be for equilibrium. So, we found Q, we're comparing them, and because it's less, therefore, reaction will shift right to reach equilibrium. Okay, so we needed to find Q. It's best to show the equation, show the numbers in the equation, and then the final answer. We need to compare them and then make this conclusion. Okay, and then we continue with the problem. So we are shifting right, so we know we are adding to the product, subtracting away from the reactant, and 1-to-1 mole ratio. So minus x, plus x, plus x. So our E row, ooh, nice math cooperation. Plus x and plus x. All right, we know our K. So now I'm plugging in my equilibrium expressions, including x. But I can see that I'm going to take this multiplied by this, both to the first power. So why don't I go ahead and start to think about the algebraic moves I'm going to make. So sure, I could write this times the same quantity, but couldn't I just square it right off the bat? And then I'll do the same for the reactant. All right, let's solve for x. So, taking the square root of both sides, and we get 2.26. And then you'll just follow through with whatever algebraic steps, make sense. And we get that x is equal to 0.387. And of course, unit will be molar on that. Then we can just apply it. Now, you've shown your work. You've shown that you have x and that these are just going to end up, being values once we apply x. And so you actually don't have to plug it in. You just could write underneath here that we have 0.613 molar, 0.613 molar. And since it's horizontal, then we know that means that, and that means that. What you also could do, of course, is say, well, the concentration of carbon monoxide is going to be equal to water. You've already shown that, and so you could just put 0.613 molar. And then, of course, adding the x here, we get 1.387, 1.387, or you could do the same thing. Carbon dioxide equals hydrogen, which will equal 1.387. And we can see just mentally that, yeah, we are favoring product. All right, so that is a great example of applying Q. Best of luck.